Good afternoon, everybody. How's everyone doing?
I'm good. How are you?
I'm good, thank you. Jadelle, I appreciate you answering me. Who was it that? Oh, Gabrielle, you got on.
Yeah, I'm here.
And Gabrielle, are you you're the one that just joined, right?
Yeah.
Okay, good. I'm glad I got that email. I just happened to be scrolling through my emails. Sophia, thank you so much. I got your email as well. I'll check it out right after class. I don't know what happened. I have to remember to double check after I've loaded something that it's loaded it correctly. So thank you for bringing that to my attention. I'll fix it as soon as class is over. I appreciate that.
Okay, thank you.
Yep. Anybody else have any other questions for me before we get started?
I don't know if you checked your email, but I sent you an email about the homework questions that I was like struggling with.
Can you, are you sending it to the right email address? Because I don't check Loyola address.
That's probably why.
You guys have to send it to my BCPS. And let me tell you why. I'm not just being lazy, but what I have to do in order to check Loyola, since Loyola uses Outlook and several layers of security, that means I have to completely log out of my BCPS credentials, which takes a long time to then go back in. That's why I can't do two emails because of the new security with Baltimore County Public Schools. So I'm sorry about that. You know what we can do, Jadelle, is you want to stay on the line afterwards and we can work together on whatever questions you had?
Yeah, that's fine.
Okay, great, we'll do that. Sorry about that. I know that must be very frustrating thinking that you've emailed me a couple times and I'm not paying attention. I promise I'll get back to you. You just have to use my BCPS email address.
Okay, thank you.
One other thing I'm getting a lot of emails about people not being able to get Wiley. I cannot help you get Wiley. You need to call Wiley. If you're having any trouble, you need to call them directly. I sent that phone number to a couple of people, but really just Google Wiley Plus customer service phone number, and then tell them that I'm a professor at Loyola and you're having trouble getting in, because 90% of people didn't have any issue at all. So I suspect you're not following directions correctly, or there's something wrong with your the way you're getting into Wiley, but they will help you. They have all the information on me, Loyola, my course numbers, everything. So if it's maybe you know, you paid for it at the bookstore and then you went on there, or they'll be able to tell you exactly what the issue is. But I cannot help you with Wiley issues. So you know the emails that I'm getting are like, I don't know what else to do. You need to call Wiley Plus and they will fix it for you. They answer the phone right away. You don't have to wait online on the line. They will fix it for you. I promise you. Okay. All right. Any other questions for me before we get started? Okay. Let's see. Let me share. I like this topic today because it brings all the math that you learned back in Algebra 1 sort of like, oh, okay, well, that makes more sense. You know, that question like you used to ask your Algebra 1 teacher, when are we ever going to use this stuff? It actually is fun to teach because it takes the stuff that you guys have been learning your whole high school career and kind of puts it into context, like this is what you need it for. So pretty cool. Just getting you guys set up on my other screen here so I can see everybody. All right, good. Now I can see all your faces. Is Thomas Boyd still here with us?
Yeah, I'm here.
Did you call, honey?
No.
You're gonna do that though, right?
Oh, yeah.
Yeah, call right after this because I think they're open till like 8 o'clock at night or something, that helpline, but they'll be able to help you right away, okay?
Okay.
All right, and let me know, email me and let me know what happened, okay? Okay, I'm not abandoning you. I'm just giving you a better solution to your question. I know you must be frustrated, but that's how you handle it. Okay, so today we're going to talk about average rate of change, which, believe it or not, you already know about, because average rate of change is slope. Let me put it in context so that when we start doing some of the calculus applications, you can revert back to, oh yeah, I know that from Algebra 1. I know all about slope. I'm gonna color code the heck out of this for you too. It really helps understand everything. Okay, last section. Well, first of all, the first section that we did is we covered like, what is a function anyway, right? When something is dependent on something else, and we talked about X and Y variables and function notation, like f of t means that t is a function of whatever the equation is, right? And then in the second section, last section, we talked about linear equations and realizing that what makes them linear is two things. First thing is the exponent, right, of the x value of the x variable is 1, makes that linear. And the other thing is that a linear equation will have a constant rate of change. That's so if you think about it in terms of Algebra 1, y equals mx plus b, where m is your slope, that means that m value is always constant, right? It's always the same. So it'll go up and over, or, you know, down and over in the same constant speed. So remember that. All right, so average rate of change is really just slope, okay? But I'm going to give it to you in a different way, and you need to adopt this new way, okay? You need to start thinking about slope like this so that when we get to the other applications, you're already thinking in terms of that. Okay, so average rate of change formula is like slope, change in y over change in t. So instead of using x, we're going to talk about t, right? Most of our applications have to do with time. We use this formula in real life, honestly. We use this formula in real life to calculate rates of change when it's not constant. And we need to keep reminding ourselves of that's what we're doing here, right? Because then when I start to ease you into calculus and show you the difference between an average rate of change and an instantaneous rate of change, you're going to be ready for it, okay? Okay. So let's look at this example down here, and I can explain all of this stuff here. All right, so here's an example. Using the figure below, they want you to estimate the average rate of change of the number of farms in the US between 1950 and 1970. So what we got here is, I'm going to write it right here too, so it's close by. We've got average rate of change would be equal to the change in, in the number, let's use n, number of farms over the change in time, in years, okay? All right, so now let's look at this first in terms of the definition. First of all, we want to do between 1950, which would be here, right? So we're looking at this point right here, and 1970. So 1970 would be here. So we're looking at that point there. So according to the definition, it's the change in y over the change in t, right? So here's the change. I'm going to use different colors. Okay, so we're gonna say change in Y would be, according to the definition above, f of B minus f of A. So that would be this vertical distance right here. And then if we take the rest of the formula, which says you're going to take B and subtract A, that would be this horizontal distance. All right, now let's look at the points themselves for a minute. The points themselves here would be, this is year 1950, the year. And this would be, I'm guessing, about 5.4. Well, actually, do we have to guess? Yeah, we do have to guess because we don't have a table. And then the other point, we know that the X value, or the T value, I should say, is 1970. And I'm going to estimate that the number of farms is about 2.8. All right, so let's label these. What we have here is this point right here is your f of A, meaning like your Y value, right? And here is your f of B. And then using that other color, pink, this is going to be your A value, and this is going to be your B value. So if you look at it and you think in terms of slope, right? Slope in algebra 2 was y2 minus y1 over x2 minus x1. That's exactly what we're doing here, right? We're taking f of B, which would be y2, subtracting f of A, which would be y1, right? Dividing by x2, which would be B, minus x1, which is A. So this is slope, it really is. They're just using it in context of with something else. So really what they're doing here with this formula is finding out, let me use a really good color here. Here. They're helping you find out what is the average rate of change going from that point, 1950, 5.4, to the other point. So the average rate of change is slope, right? Now, if you think about it, that's not a very good indicator of what's going on in that whole graph, is it? Right? You can't say like, okay, just because the average rate of change is the slope going from that point to the other point, there's some other stuff going on, right? And in calculus, what's going to happen is eventually we're going to start analyzing rates of change at particular points along a graph. So what's going to happen, and this is so exciting, but the distance between 2 points is going to get smaller and smaller and smaller until you can actually calculate the instantaneous rate of change, which is what calculus is all about, or one of the things it's all about. All right, so see, I get excited about teaching this because it actually does eventually make sense, but you have to trust me with the algebra 1 stuff and slope. Let me slowly get you to that place. All right, so rather than using our slope formula, because I want to really encourage you guys not to think of that. I want you to start thinking in terms of calculus. So let me get rid of that in the notes. And instead, let's use this, and let me just write it lower so we can. Okay, so we're looking at the change in the number of farms over the change in the time would represent the average rate of change. And we're going to just use the formula above, which says f of B. Our f of B value is 2.8. Subtract, according to the formula, f of A, and our f of A value is 5.4. divide that by our B value minus our A value. So that would be just 1970 minus 1950. So you would get negative 2.6 over 20, which equals negative 0. Oops, let me make that more legible. 0.13. And of course, we're in millions here, right? And since we're doing rate, right, we want to say million farms per whatever your x-axis is, or per year. Now notice this is decreasing, right? Which should make sense because that orange line I made is decreasing, right? Remember, when you're reading graphs, you're reading, always when you're reading graphs, you're always reading it from left to right. So you're reading it like left to right. And see, when I'm doing that, see how it's decreasing? That's how you know it would make sense then that your average rate of change is a negative number, right? Because your graph is decreasing. Let's spell that right though. And then of course, I'm telling you the tricks of the trade with Wiley. Wiley will either give you that word, in which case your answer would be negative 0.13, or if they didn't give you that word in the answer, and be careful, you'd have to just move the decimal point over 6 times to get 130,000 per year. All right, any questions so far? Do you guys see how it really is just slope? Everybody okay? Can thumbs up, thumbs down, sideways? How are we feeling? Awesome. Good, good, good. Thank you for trusting me on this. You guys, I feel like you're with me, and that's good. Trust me on this, and then the rest of this course will be easy for you. Okay, example 2, find the average rate of change between two functions. Now here I gave you the actual graph, right? And then you were kind of estimating the numbers. Here I'm giving you two equations. And remember, we can represent functions in a lot of different ways, with tables, with graphs, with words, and with the graphs themselves right here, right? All right, so we're going to do that same formula, only now I'm going to do it using the average rate of change and the formulas themselves. So the average rate of change would be the change in y, or we could even say f of x, over the change in x. So we're going to say we want f of 1 here minus f of 2, so negative 2, which would be here. So notice that this is my b value and this is my a value, right? So f of b minus f of a all over actually b minus a. And I'm just using the formula itself, right? So b is 1 minus negative 2. Okay. So on the top here, we have function notation, right? And finding f of 1 just means for you to put 1 everywhere you see an x, right? So we're going to put 3x squared plus 4, and then we're going to subtract 3x squared plus 4. But the tricky thing about this is that we're subtracting the whole thing. So let me grab a different color pen because this is important. You need to put parentheses around the entire second thing. So f of 1, we had, grab a color here. f of 1 goes here. And f of negative 2, well, that's not a very good color. Make it a better one that shows up. F of negative 2 goes here. And then 1 minus negative 2 is just positive 3. Okay, so simplifying that, we have 3 times 1 squared, that's 3 plus 4, that would be 7. And then we're going to subtract the result of that parenthesis. So we've got negative 2 squared, so that's positive 4. Positive 4 times 3 is 12, and 12 plus 4 is 16. We have 7 minus 16 over 3, which is equal to negative 9 over 3, or equal to negative 3. Okay, so we've got that, and that's the first part. Find the average rate of change. So the average rate of change of the function 3x squared plus 4 between negative 2 and positive 1 is equal to negative 3. Then it says to illustrate your answer graphically. This is why I like this section so much, is because it's like, okay, you can see how all of this algebra actually relates in real life. All right, so if you graphed this 3x squared plus 4, it would end up being a parabola, as you know, from quadratics, right? Parabola going through the center. Obviously, it's raised up 4 units. Not that you guys have to remember transformations right now, but if you remember, this outside 4 raises the parabola up 4 units, right? And then that 3 next to the x squared makes the parabola a little bit skinnier. Not that you have to know that. I'm just trying to pull back what you remember from. Let me make this parabola a little bit skinnier. All right, so f of negative 2 would be, let's say here's negative 1, negative 2. So that would be that value right there. And then f of positive 1 would be this value right there. So what we have here is we have the average rate of change, or the slope, from one point to another point. So all we just did is we found this slope. And we did it using average rate of change. We're going to, remember, keep using this average rate of change and gradually get you to what the whole calculus instantaneous rate of speed or rate of change means. Any questions so far? We doing okay, everybody? Okay. All right. Oh, and notice this too. You see how this is a negative rate. And notice that this is a negative slope. Right? Or what I like to call rate now. So it makes sense, right? That's how one thing is related to the other thing. Because all this is really doing, guys, is it's taking, if you look back at the formula, it's the change in y values, right? Which is what your f of x is. And your y value is what happens to y when you put x in the equation, right? So it is slope, but we're just using a slightly different formula. All right. Any questions at all?
I have a question.
Go for it.
Oh, can you hear me?
Yeah.
Okay. So I was just wondering, why did you, is this like, did you just write like the parable, like the line, just like as an example, just to place the 2 points on the line, or is that the line they would make?
That is the line they would make, and this is what I know, right? Because I know that the parabola definitely looks like that, right? I know that this point right here would be at -2 and some y value, right? And then this point right here would be +1 and some y value. So to make that sketch, that's a pretty good sketch of what the actual line would look like. to find the Y value, Jadelle, and I don't need to prove this point, but to find the Y value, all you'd really have to do is calculate that, right? Because that would be the Y for positive 1, and this would be the Y for negative 2. Make sense?
Yeah, it does. Thank you.
Good, good. All right, this is so fun for me. Is it fun for you guys too? Maybe not as much fun as it is for me. All right. All right, so here's another example of where we can use this sort of intuitive kind of like, how does one thing relate to another? So here it says, when a deposit of $1,000 is made into account paying 2% interest, compounded annually, the balance B in account after T years is given by that function B equals 1,000 times 1.02 raised to the T power. Now, this is not a quadratic equation anymore. Anybody know what that's called? What's it called when the exponent is a variable? Anybody remember?
Exponential.
Yeah, that's exactly right. Thank you, Dylan. It's an exponential function, right? So, and remember, we're doing average rate of change, which is really a linear operation. So how does that linear operation work on this exponential graph? Well, it's just measuring one point on the exponential graph to another point on the exponential graph. We just were interested in the difference and the linear relationship. Okay, so let's see what we got here. First, just so it's handy, the formula for average rate of change, I'll put it here. We've got change in Y over change in X equals F of B minus F of A all over B minus A. All right, so we want to find the average rate of change over this interval. So we're going to say change in B over change in T, right? The variables they're giving us is going to be equal to the balance when it's 5 minus the balance when it's 0, and we're talking time, all over 5 minus 0. So this is your B value, and this is your A value. And that is to the T power. Yeah, good. I just had a little typo there, but it looks like I fixed it. All right, so all we do now is take our exponential equation, 1,001.02 to the T power minus 1,001.02 to the other T power. And remember, like I said before, it's important to use my flashy pink to do that whole thing before you do any subtraction. Okay, so let's see. It says B of 5 minus B of 0. So B of 5 would go here, and B of 0 would go here. And then we're going to divide that by 5 minus 0, or 5. So if you do this calculation, you'll get, this should be 1,000, 1104.08 minus 1,000. Since anything to the 0 power is just 1, right? All over 5. And then that would be 104.08 divided by 5. And all of these little numbers are going to mean something in a minute. So you end up with dollars, right? Which is the balance, remember, over time, So that's how we know that this is dollars, or $20.82 per what?
Is it per years?
Yes, and what's your clue for that?
Because it said compound annually and in the
Yes.
account after 2 years.
Yes, that's exactly right. And that's the kind of thing you need to be really careful when you're doing these problems, is read it carefully, right? You don't know if it's, well, is it, per year? Is it compounded weekly, or is it quarterly, or whatever? Those words tend to be very important. Okay, so that's just plug and chug, right, in the formula. But let me show you what it really looks like. I'm going to move this down a little bit. Okay, so let's look at the graph itself. We've got, and I'm going to exaggerate this graph too. Let me grab a pen first though. Okay, so let's say graph looks something like this, where this is 0 years, and let's say this is 5 years. The graph will look something like this, like an exponential graph, right? Something like that, where this amount right here ends up being 104.08. Notice that's the same as this value right here, right? That would be 0 and that. And then this at 5 would end up being, wait, actually I'm drawing that not as a point, sorry. That's not what I mean to say. And I don't like my drawing either. Let me make the drawing better. I want it to look exponential here. So here we go. And it would look something like that, where this is 0, and let's say this is 5 years. So here's our point at 0, and here's our point at 5, right? I'm just finding that point there. So that what we just found out, this rate is really just the slope. And notice that it's a positive slope, right? So this would be the equation of y equals 1,000, 1.02 to the x power. And I'm using numbers that you could put in your calculator, or if you're using Desmos, right? So you would get that graph. And the 104.08 would be right here. So the difference between 5 years and 0 years would be 104.08. But once you divide that by 5 years, these 5 years here, that's how you're going to get your per year rate.
I have a question. So
Okay.
you said you have to divide 104.08 over 5 to get like your rate of change.
Mm-hmm.
Okay. All right. I was
And
just confused.
excuse me, all I'm doing here is this, let me erase this so we're clear on what I'm saying here. If you use the formula for rate of change, I'm just simplifying the numerator, right? And then you would get, if you did 1104.08 minus 1,000, that's where you're going to get 104.08, right? And then over 5. But I'm trying to relate to you what that means in terms of this graph, right? So the distance between the y distance here is 104.08, right? And the X distance here is 5, which should make sense because that's what it all simplifies to. Okay, any questions? Anything else? All right, so we did it, let's see, we did it with an actual graph, an equation, words, and now we're going to look at a table. All right, so here it says, what's the average rate of change in tobacco production between 2003 and 2015? So here's our data on 2003, and here's our data on 2015. So if we just draw a really crude graph here, we could say if we're only interested in those 2 points, we're interested in, let's say 2003, and let's say this breaks up. So then we have 600, and then up here, like 900 is the highest number, highest, right? 6, 7, 8. So if I were to graph 2003 number at 803, it would be somewhere like right above 800, right? And if I were to graph 2015 data, that would be at 711. So let's say this is 2015, and that's at 711. So that would be a little bit higher here. If all I'm asking you for is the rate of change, I don't really care what's happening to the rest of the graph. It could be going up and down or whatever, right? Anything could be happening. All I'm asking you for is how it's changing from one point to another. So really, I'm just asking you for the slope of that line, right? Well, that's simple enough, right? We can say the change in P production over the change in time here is equal to 711 minus 803 over what? You guys tell me. How can you calculate the change in time?
Is it 2015 minus 2003?
Yes, it is. So this would be your f of a value, right? And this is your f of b. And you know that 711 is your f of b because it happens later than f of a. So if you're having trouble like which one is b and which one is a, b is always the one that happens later in time. Okay, so what do we get? Negative 92 over 12, which is equal to negative 7.667 million pounds per year. So remember, what if we graph the rest of those points, right? They could be everywhere, right? So your graph really, it could be doing that, but what we're asking for is the average between 2 very specific points, which in reality, not all that useful to us, right? It doesn't really describe the graph very well, especially if the graph looked like what the pink thing that I drew in there, right? That's why you need calculus, okay? So remember, we're going to go from what you do know about slope, gradually bring you into the calculus terms, and then we're going to go for instantaneous rate of speed. But my point here is that this average rate of change it's not very useful because it really does not describe what's happening in that graph, right? And it might be in certain business matters, you might be interested, let's say you're interested in maybe not the 2 years, but you're really interested in what exactly is going on at that particular point, right? Because let's say you happen to know that you're going to be able to get the materials for the furniture you're building, like at this time, I know that I've got a whole bunch of leather coming in, for example, right? If I know certain factors ahead of time and I can predict where the graph is going to go, then I can just make much better business decisions. Like I can make a decision on how many sofas do I think I can sell, and if I've got all of this fabric coming in. So there really is a very real use for this calculus stuff in business. And I assume all of you guys are business majors, right? That's why you're taking applied calculus. Are you all business majors? Yeah, so it has a very real and interesting application. All right. But right now, all you really have to know is how to calculate this rate of change. Okay, now here it's asking you, during the 12-year period, are there any 1-year intervals during which the average rate of change was positive? So notice that here, if you just look at, and this kind of proves my point, if you're just looking at these 2 points, you would say, okay, there's a negative trend, right? But actually in this data, there's several positive trends that you're going to miss altogether if the only values that you're calculating are those 2 points. So let's see. Let's look at when it's increasing. I'll tell you screen. Okay, so between 2003 and 2004, it increases, right? It decreases between 2004 and 2005, but then it increases again between 2005 and 2006, again between 2006 and 2007, again between 2007 and 2008, again here. Let's see, what about the bottom? Let's see, from 2010 to 2011, it falls, right? But it starts gaining again. And then it falls between 2005 and 2006, but then it gains a lot here. And at the very end of that year, the 2015 year, it's come down by quite a bit. But if you look at the overall trend, probably most of the time, the overall trend was actually rising, which is why we need calculus, right? We have to have calculus because average rate of change just doesn't get the job done. So that's kind of their point in asking this question. So it increases between 2003 and 2004, and then also from 2005 all the way through 2009. It also increases from 2011 to 2012 and 2013 to 2014. So what calculus is going to end up doing is it's going to let us explain or summarize what's going on in a graph in better detail than this will show you, because this clearly, although it's a negative trend, if you look at that line, a lot of what's going on here are positive trends, which you as business majors would be interested in. Any questions so far? You okay, Matthew? Okay. Sometimes I do this too when I'm like really concentrating, you know, where you're like totally focused in on something, but you look like you might just be tired. You're okay? All right. Anybody have any other questions for me so far? Everybody feeling okay so far? I don't mean to call you out, Matthew. I just worry about you guys. I just want y'all to feel good about this stuff. Okay, we're cool? Felipe, you're making fun of someone. I can see it in your eyes. You are. All right. All right, so let's go on to some stuff that you may not have heard of, right? All this other stuff up until this point, you probably have heard a lot of these terms in terms of like, you know, slope. So let's go on to something that might be new to you. Unless you've taken like AP Calculus, you may not have heard these words where you can describe graphs with concavity. So concave up would have either this shape or this, or this shape, right? And how I like to remember concavity is, think about like if something's in a U shape or part of a U, it's concave up, right? Same thing with concave down. They show you these two separate sides of it, because we're going to talk about increasing and decreasing. But when I think of concave down, I like to think of if it's part of a, you know, upside down U, right? So you need to be able to describe where on a graph something is concave up or concave down, and also where it's increasing or decreasing. So on this side here, we've got increasing there and increasing here, right? Because remember, when you read a graph, you're going to read a graph from left to right, right? And then, of course, it's decreasing on this side of the concave up. There. Okay, so let's use what we know there to look at this graph. So we want to know where on the graph is it both increasing and concave up? There's a couple places, but can you guys tell me, just use the letters as the endpoints? Concave up and increasing.
From A to B.
That's actually from A to B. You're right, it's increasing from A to B, but it's actually concave down, because look, see how it's part of a upside down U? So you're right about the increasing part. So where is it concave up, which would be part of a right side U, right? And also increasing.
D to E.
Yeah, D to E, right? Because here's that concave up shape and it's increasing. There's one more place where it is concave up and increasing. What's that?
H to I.
Yeah, good. Okay, now let's do another one. Where is it increasing and concave down? Sean, what do you think?
What I said before, A to B.
There you go, A to B. Do you see why now?
Yeah, I see.
Yeah, because here it is, part of a like upside down U shape, right, for concavity, and it is increasing because when you read it from left to right, it's going up. Does that happen anywhere else on the graph, Sean?
E to F.
Yeah, very good. I think you got this. All right, now we want decreasing and concave up.
C to D.
Yeah, good job, Jesus. C to D. This is concave up because it's part of a right side up U, right? Does that happen anywhere else?
Would it be F to G?
Let's see, we want concave up. So not from F to G, but actually from G to H. Because I would argue that F to G is concave down. So that kind of gives us our last little answer, which is, let's see, I want to make these colors really different so you can see when I print it. So concave down, but decreasing would be this one right here. And this one. See how the color will help you later? Color, I love using color. Any questions on concavity or increasing or decreasing functions? All right, good. We're doing okay? Sideways. All right, Dylan, can't see you, so I don't know if your thumb is up or down. Sophia? There he is. Awesome, thank you, Dylan. And Sophia puts her thumb up, okay. Okay, so here's another example. This table gives values of a function. W is equal to f of t, which means that W is a function of t, whatever W is. Let's make something up on W, probably weight, let's say. Weight is a function of time. So does this function appear to be increasing or decreasing? So first tell me that. Is this, if you were to graph those points, does it appear to be increasing or decreasing?
Would it be decreasing?
Oh,
Yeah, decreasing. Can you tell me why you think that, Tom?
Because W, which in this case I guess is Y, is going down.
Yeah, very good. It's going down. So if you graphed those, it would, and matter of fact, let's make a little sketch for this. Just 'cause I think it'll help you. So if this is 0 and this is 100, this graph is going to end up looking something like this, where let's say this is, what do we want to make that? 24. And let's say, I don't know, we're talking seconds or minutes or something. So some unit of time. And then this would be your weight that we said W is like, let's pretend it means weight for a minute. Okay, so what we do know is it is decreasing. Or actually, let me give you the formal reason why. That would be better. Okay, as T increases, right, as T gets bigger, notice if T is getting bigger if I go this way on the graph. So as T increases, W decreases. So it is decreasing. All right, then the other question was about concavity. Does this appear to be concave up or concave down? Now, I want you to know that obviously you can say that this is concave up, right? Just by looking at my sketch. But let me tell you why I sketch it like that, because you wouldn't necessarily know that unless you graphed all the points out, right? But what's basically happening here is the rate decreases. And this is what I mean. Notice that the difference between 100 and 58 is 42. The difference between 58 and 32 is 36. The difference between 32 and 24 is 8, and so on, right? So the difference between the values is decreasing. So what that means is that it's slowing down, right? So notice here how the slope is very steep, right? So that would maybe represent the difference between 100 and 58. So the change in Y value happens drastically quickly, right? And then it ends up slowing down, right? And slowing down even further. So that's how I know that if something starts out with a really steep difference and then slowly the rate changes, that's how I know, oh. So when the difference is slowing down, you're going to have concave up. But if the difference is doing the opposite of that, you would have concave down. And I'm going to show you an example of that. So let's see, let me finish my notes here. The rate W decreases gets smaller. Which also means the rate slows down. Or if you can think about it, the rate as slope, it will be less slope, right? So the steeper the slope, the higher the number, right? When slope changes, the lower the number gets, right? Okay, rate slows down, so it's concave up. Now I'm going to give you an example of, what the numbers might look like if you had concave down. Everybody good so far? All right. So here's an experiment that suggests that the male maximum heart rate, which means the most times a heart rate can safely beat in a minute, meaning like if you're exercising or you're at the gym, there's a formula that's something around like if you take your age and subtract your age from 220, you should not have your rate, your heart rate any higher than that, or it's dangerous for your heart. So let's say, I'm going to draw a little picture because pictures always help. So let's say pretty high heart rate is around 220. Okay. And what they're saying here is that in the first 21 years of a male's life, the heart rate can go down by 9 beats a minute, right? So the older you are, the lower your heart rate should be while you're exercising, right? You hear about like older men in their 40s and 50s having heart attacks on the treadmill and stuff, and that's why. It's because their heart rate is up too high. All right, so let's say this is 220, and then the difference here would be 9 beats per second, right? So here they are at 0, here they are at 21 years old, and then here they are at 33 years old. So the difference here would be 9, so 220 minus 9 would be 211. And then and then their heartbeat as they age needs to change by 26. And here they're saying here by 26 beats per minute during the first 33 years, right? So the graph would look something like this. So we've got 220 up here, and then age 21, right? And then age 26 would go here, right? So what happens here is it speeds up, right? Or the slope is steeper. So the graph won't really look like that, right? It'll look more like this. So is that decreasing or increasing?
Decreasing?
Yeah, definitely decreasing, right? Because if you read this graph from left to right, right, from this way to this way, it's decreasing. And like I told you, this is going to be a concave down. So you can say, to summarize the rate, it decreases, which would be 26 beats per minute, gets larger from where it was down at, 9 less than 220. So the rate speeds up. All right, so hopefully that's a good, you can see the big difference here, right? Here, the big difference here means that you have a steeper slope, right? And since it's decreasing, that's how you know it's concave up. Here, it's slow at the beginning and then speeds up. So that tells you that it's going to be concave down, and of course we know it's decreasing. All right, next example. Interpret the expression in terms of Arctic Sea ice extent. This word ice extent, this means area covered by ice. So interpret the expression in terms of Arctic Sea ice extent. Oh, it does say that. I think I put that in later after I did that. Okay. Let E of X be Arctic Sea ice extent in millions of square kilometers. And there's where, remember, Wiley's very picky. Be careful with that. As a function of time in years. So we know that E to the X is, it's a function in terms of time. So the area, we can say, let's say area with this time is equal to this amount here. What's that mean? Let's write it so it's in the right order. A is equal to E of T. So if you say, what does this really mean? We can say that, well, actually, what do you guys think? I just want you to tell me in words, what does E of 29 equals 15 mean in words? Well, area is 15, right? So you can say that 15 million square kilometers is covered by ice in what year? So I think you're kind of doing this right. So this is since 1979. So this calculation would be 1979 plus what?
29.
29. So isn't that 2008, right? There, I do make mistakes occasionally. So if you know you're right, then just say, no, actually, that's not right. Say, this is the right number. But I think that's correct. And that's it. Now, B, we're going to explain this. So E of 29 minus E of 4. What does that mean? Divided by 29 and 4. So this is average rate of change, right? So what this means is over 25, which I'm calculating by taking 29 and subtracting 4, right? Over 25 years, the area covered by ice, did it increase or did it decrease?
Decrease.
Very good. And how do you know it decreased?
It's a negative.
Thank you. By 40,000 square kilometers. And I'm getting that by taking 0.04 and multiplying it by a million, or moving that decimal place over 6 to the right. And there you go. So over 25 years, the area covered by ice decreased by 40,000. And that's just doing slope, right? The difference between the area at 29 minus the area at 4 divided by the number of years. Okay, now I told you in calculus, we use a lot of time problems, and particularly in your area of business, it's definitely something we're very interested in. So this average velocity term here, this is a type of rate of change. That in particular deals specifically with distance and time. Okay. Velocity, we can say, is another way of saying speed, right? How fast is somebody going is their velocity. Guys, 1 second, I'm going to let my dog inside. She's spoiled rotten. All she has to do is scratch and I'll let her in. Okay, so think about this for a minute. If we have distance and time, and let's say we want to measure the average rate of change between this point and this point, that might be, let's say this is hours, say this is, well, I probably don't need to give you that much. Right, so average rate of change or velocity between 2 points is useful, but if you really wanted to know how far somebody traveled, right, let's say that sometimes they're on a bike and sometimes they went fast and sometimes they went slow because they were going uphill or downhill. The actual distance isn't really measured by the Y value at all, right? It's much more than the Y value. Okay, so, but it is helpful, right? And it does help us do some things. So here we go, we're doing a table this time. So we want to find the average velocity of a grapefruit that's being thrown in the air over a particular interval with t equals 4 seconds to t equals 6 seconds. Let's draw a picture of what that would look like. First, I'm going to just sketch. Let's see, that looks like the highest is about 162. And the lowest, of course, would be, let's just call it 0. Let's see. What are we interested in? We're in, well, let's draw all 6 of them, actually. That'll make more sense for you. So let's see, that's 3, 1, 2. Yeah, so that's all 6 intervals. And if we just plot these points, so 0, 6 would be way down here. 190 would be, let's see, that would be somewhere like that. And then 2, 142 would be higher. And then 3, 162 would be all the way at the top there. 4, 150 would be a little lower than, let's see, a little higher than 140, somewhere around there. I'm just like estimating. And then let's see, 4 and 150. 150 is a little bit lower here. And then the last one, 1, 2, 3, 4, 5, 6 would be 6 and 30. So it'd be somewhere low. So you can see how it makes basically a parabola, right? So it makes sense that if you throw it from 6 feet off the ground, right, into the air, it's going to make a parabola-like shape, right, as far as how high it is in the air. So if we want to find the average velocity, we're going to do the average distance over the average time between 2 particular intervals. And in this case, we're interested in t is 4 and t is 6. So we're interested in these 2 points. So 1, 2, 3, 4, 5, 6. So see how we're really just calculating, even though we've got a parabola, we're really just calculating the distance, or not the distance, sorry, the slope of that. So using our formula, we could do 30 minus 150 over 6 minus 4 to get negative 120 over 2, which is equal to negative 60 feet per second. Now there's some use to that, right? Because if you throw a ball up in the air, right, you could, for example, calculate the difference like between here and here and get the average speed when it goes up in the air, right? And then our values, our green values would be calculating the average velocity as it goes, down with gravity. Of course, it would be going faster. So there's some validity to using average velocity over a period of the graph, right? But again, if I wanted to calculate between, let's say, this and this point, then that's not very useful to me, right? Because that's not the path of a projectile. The path of a projectile goes up and down again. Trying to really stress the meaning as I'm going through this really simple stuff so that when we get to the word problems, you guys will be like, I remember you talking about that. All right, any questions so far? So don't forget that velocity is just a type of rate of change that deals specifically with distance and time. That's the only difference between the rate of change that we've been talking about. All right, example 10. Car travels away from home on a straight road. Its distance from home at time t is shown in the figure. Is the car's average velocity greater during the first hour or during the second hour? So here's the first hour, and here's the second hour. So if I was going to find the average velocity between 0 and first hour, it would look like that. That's the first hour. And then if I was to find average velocity, let me use a totally different color so you can see it. During the second hour, I would find average velocity from there to there, and it would look like that. So the question is the velocity a bigger number, or is it greater during the first hour or the second hour? What do you guys think?
I think the first hour, because the slope's steeper.
That's exactly right. It's absolutely during the first hour because it's steeper there. So the velocity is going to be greater than it would be if the slope is less steep, right? Okay. What time is it? It's 4:15. Can you guys hang in there with me for one more example? Remember last time I let you out early. Okay. And I promise I'll do that. Sometimes it's just better to get it all done. So we're talking about relative change now, and it's just a real simple formula. And the formula just says that relative change would be P1 minus P0 all over P0. And when I shouldn't say zero, I should say P sub 0. And P sub 0 or Y sub 0 or T sub 0 is always like your initial starting point, right? Think of P sub 0 as like a Y-intercept, right? It's like your initial point where you start something. So the number of sales per week of this pair of jeans is 25 pairs, right? Which is what it was in 1 week, right? The initial amount of pants that they sell is that. And then it goes up when the price is reduced later by a certain amount, right? So here's your P sub 1. So just using the formula, P sub 1 minus P sub 0 over P sub 0, you're going to get 45 minus 25 all over 25. And that will give you a percentage, which is, let's see, this is 20 over 25, which is equal to 0.8. And when you give relative change, it is often expressed as a percentage, right? So here, we're going to say 80% sales grow by 80%. Now, this is, what was the topic of this? I took this when I was in college. Like economies of scale, because I was a business major too, once upon a nature of a young student that I was. What's it called? Oh, I forget. I'll think of it. I'm gonna look on my transcripts because it's a very interesting class that you guys will all take like your senior year. And it really does put all of this business stuff together for you. So it was one of my favorite classes though. All right, so that's simple, right? Here in this example, a stamp goes from initially being 47 to being 49 cents later. So using the formula, P sub 1 minus P 0 over P sub 0, you're just going to take 49 minus 47 and divide it by 47. So you'll get 2 over 47, which is equal to 0.043. Now it's usually expressed as a percentage, so this would be 4.3%, and this is an increase as well. It would show up as a negative number if it was a decrease. And I just added these two. So if you printed out these notes ahead of time, I ended up adding 2 more after looking at the Wiley problems, because sometimes they give you P0 and P1, and sometimes they'll give you P1 minus P0, like the whole thing, like in this case. So notice the formula is P1 minus P0 over P0. Well, we know the original population is 9734, but here they're saying that it increased by 1,200 people, right? Which means that it's giving you this entire amount of increase. So that's why you put 1,200 in here. It's just the wording, so you have to be careful for that. So we would get 0.1233, which is equal to 12.33%. This last example, they are giving you P0. This is the original price of the car. And then it goes down later, which is a later value for the car. So we can just use our formula straight up here. So we've got 59,000 minus 65,000 over the original 65,000. So you'll get negative 0.923, or a decrease of 9.23%. So just be careful how they word things. And remember, with Wiley, you'll get used to it and it'll make you a better reader. I promise you. Wiley is a very good comprehensive program, and it'll teach you how to think in terms of calculus. But you have to like accept that. You have to accept that you have to be very careful with the language, and they're gonna test you on, you know, the word million or even the word percent, right? So just be careful with the decimals and the percent and the word millions. And, you know, if they give you like, it's in billions, then take that into account and look for the word billion so that you know whether you're going to answer with a decimal or 9.23, and then they put the word percent in, if you understand what I'm saying. So just be careful with the language. All right. I know I kept you for 6 more minutes, and I think I let you out early last time. So we'll go generally the time that we're scheduled for, but this was a big topic and I wanted to cover it all in one day. So, all right. If you guys have any questions, make sure you email me at my BCPS email address. Okay. We can always get together. Just don't email me at midnight and expect me to get back to you, because that's probably not going to happen. And remember, I do have a day job too. So, but I do have free time during the day that I could help you. Just email me with some notice and I will definitely, we can jump on this site again. All right, so yeah, Felipe, you have a question or you just saying goodbye?
Thank you.
Okay, thanks guys.
Thank you.
All right, have a good weekend. I'll see you on Monday.
I have a question.
Yeah, go ahead, honey.
It's regarding the first assignment is due on tomorrow, right?
Yeah, the 28th, I think at midnight, right?
Yeah.
Yeah,
So
and Janelle, just so we're clear on this, all of those dates are in the pacing guide.
yeah, it's just that Wiley had it due for the 20th, and I was like, I don't know if that was the right one or not, but I see.
All right, you know what? While I have you on the line, let me check it out because it
Yeah.
should be the 28th. Let me look at it real quick. Don't go anywhere.
Wiley changed it.
Okay, it changed it. Yeah,
Yeah,
it was earlier.
Oh, okay.
But that's not my question. My question is regarding one of the thingies.
Okay.
Professor, if I could ask just a quick question.
Mhm.
Okay, so on Wiley, they had one of the last class. We never went over the last problem, and
Yeah.
it was like this blue thing. It looked like a web or something like that. On
That's one of
Wiley,
my
they had a
questions.
problem just like that, but we never went over it in class. So I didn't know how to do it.
Which one was it?
It was in 1.2. Jadelle, do you know which one I'm talking about?
Yeah, I have it pulled up right now. Let me go back. I'm like
Okay.
looking at the
Give me
questions.
1 second so I can pull up Wiley real quick, okay?
Yeah.
Okay.
That's not it. That's
Okay, I found it. It's
okay.
it's the 1.2 question 009.
Okay, thank you.
All right, I'm almost there.
Okay.
Oh, okay. Let me grab something here and I'll just. Okay, so basically they're asking you if the slope is greater than 0 and if the y-intercept is greater than 0, right? So let me look at the answers again real quick, sorry. Okay, match the lines to the conditions on the parameters M and B. Yeah, okay, So let's take this line right here. Right? The slope is, which is M, is going to be positive, right? Would you agree?
Yep.
Okay. The other line that would be positive would be this line. Okay, so slope's positive in both of those, but the only one
Y-intercept.
has, yeah, is y-intercept that is a positive y-intercept would be here, right? Because the y-intercept here, so this would be B is positive, down here would be B is negative.
Okay.
Is that better?
Yeah, that makes sense. Thank you.
Because then you could do the slope is negative here and here, right? Is less than 0. So then you're just going to see if the y-intercept is above or below.
Okay.
Jadel, what is your question?
I have another one about this one you just did. Are you saying that the line that's under, like the one that you underlined, are you saying that one is like lower than 0?
I'm saying that both these lines, L1 and L2, have a positive slope.
Oh, okay. Okay.
Which means that their M value is greater than 0. The point
Okay.
here on this L1, this is a y-intercept that is greater than 0, right? Because it's above the x-axis.
Yeah,
This one has a y-intercept that is less than 0.
because it's lower than it.
Say that
Okay.
again? Yeah.
No, because it was lower. It was lower than the actual.
Correct, yeah. Well, because of the space where it is right here, right? So think about if this were on a graph by itself, you could say, well, this graph is positive slope, but the y-intercept is below 0.
Okay. All right. The question that I had, it's when it like gives you an equation, says determine the slope and the y-intercept of the line of whose equation is given. So for example, it gives you like 9x plus 2y equals 8. Like,
Can you
what would
give
I
me-
do?
Can you just tell me what number it is? I can pull it up. It won't be the same as yours, but it'll be similar.
It's question 6 of 1.2.
Okay. Like this?
Yeah.
Okay. So in order to figure out what the slope and the y-intercept are, you have to get it in y equals mx plus b format, right?
Yeah.
So that's the slope. And this is the y-intercept,
Okay.
right? So we need to take this equation, 7x
Make it
plus
to-
2y equals 4, and make it equal to y. The first thing we'll do is get rid of the 7x.
Oh, okay.
Y equals negative 7x plus 4, then what would we do?
What do we divide?
Divide both sides by 2.
2.
So you get y is equal to negative 7 halves x plus 2. So what's the slope?
The slope is negative 7 over 2.
And the y-intercept is 2, right?
Yeah. Well, wouldn't it be negative 2?
No, this is a positive 2.
Okay. Okay. Sorry. All right. I get it. I confused myself. I see
No
what I'm doing
worries.
next.
No worries.
Sorry about that. All right. Thank you.
Okay, have a great day, sweetie.
You too.
All right, bye.
Bye.